Howdy, in this video we will conclude section 2.5 of the Suppes and Hill textbook. The main thing that's new here is De Morgan's law, so there's going to be a lot of focus on that. As we progress through propositional logic, it's a good idea to step back and review what we have covered. Here are some of the rules of inference and some so-called equivalencies. I start out with Modus Ponens and then with Modus Tollens. For a so-called mixed hypothetical syllogism, those are the only two valid types of inferences. Modus Ponens, we have if P then Q. P is the case, therefore we can conclude Q. If it is raining out, then it is cloudy. It is raining out, therefore it is cloudy. P is sufficient for Q. P here is the antecedent, Q here is the consequent. For Modus Tollens, we have if P then Q, not Q, therefore not P. If it is raining out, then it is cloudy. It is not cloudy out, therefore it is not raining out. The consequent Q is necessary for the antecedent P. Double negation is a equivalency where P is logically equivalent to not P. We have that double negation there. So P, not P are equivalent. From not P we can get P. I like logic, therefore it is not the case that I do not like logic. The conjunction is a situation where we have a premise such as P, another premise such as Q, and then we can combine them through the and sentential connective to form the conjunction P and Q. I will have eggs. I will have bacon. Therefore I will have eggs and I will have bacon. Next we have simplification. If we have the premise P and Q, we can simplify to get P by itself. A lot of textbooks you can only simplify the first term, not the second one. The Suppes and Hill textbook allows you to infer either of them. It just depends on the textbook. It's a matter of convention. It is Saturday and it's hot outside. Therefore, it is Saturday. Next is the disjunctive syllogism. Here's a version and here's a version. You have a disjunction in there, P or Q. The next premise denies P, so Q must be the case. Some textbooks you can only do this first type of inference, not the second type. That is to say, you can only deny the first term to thereby affirm the second term. Either it is moving or it is stationary. It is not moving, therefore it is stationary. Addition is another inference. We start with the premise P and then we conclude P or Q. This works because we know P is the case, and so this disjunction must be true, right? The desk is brown, therefore the desk is brown, or Jupiter is a planet. That's valid, even though Jupiter, of course, has nothing whatsoever to do with my desk. The hypothetical syllogism, if P then Q, but if Q then R, therefore if P then R. There is, so to speak, a chain reaction. If I go to work, then I will go to Starbucks. If I go to Starbucks, then I will buy a coffee. Therefore, if I go to work, then I will buy a coffee. We have our constructive dilemma. First premise, P or Q. Second premise, if P then R. Third premise, if Q then S. Therefore, our conclusion, R or S. We end up at a disjunction because if P is the case, then R will be the case. But if Q is the case, then S will be the case. So it must be R or S is the case. Either it is cloudy or clear. If it is cloudy, then I see a gloomy sky. If it is clear, then I see a blue sky. Therefore, either I see the blue sky or a gloomy sky. We have the commutative rule. This is just an equivalency. P or Q is logically identical to Q or P. P and Q is logically identical to Q and P. The order doesn't matter. It is Saturday and it is hot outside means the same exact thing as saying it is hot outside and it is Saturday. And then we have our tautology. P or P, therefore P. It is raining or it is raining, therefore it is raining. Here's what's new. De Morgan's laws, or DL or DEM for short. This deals with the negation of a pair of conjuncts or disjuncts. I remember a professor of mathematics once saying that this is the most confusing of the laws in terms of propositional logic. However, it's not too bad. The reason it's confusing, I believe, is that people often look at this stuff as just plain symbols with arbitrary meaning and as just a process of algorithmic tools where you manipulate these symbols. But don't do that. The best thing to do is understand these symbols have meaning, they have content, and then it's not confusing at all once you get the hang of it. It's true that, for example, if you have the statement minus parentheses a plus b, close parentheses, that you can distribute the negative sign in a straightforward manner to get minus a minus b. That's obviously true. But it turns out you cannot do something so straightforwardly here. For example, if you have the statement p and q, and you were to, so to speak, collectively deny that, so it's not the case that p and q, that would be logically equivalent to the statement not p or not q. You have a disjunction. So it's not just that you're denying the p, you're denying the q, you moved from this conjunction to this disjunction. And we'll think about this meaning a little bit more in a minute. How about if you have a disjunction, p or q, and you, so to speak, collectively deny it? So it's not the case that p or q, that would be logically equivalent to a conjunction, not p and not q. So here is our disjunction, but here is a conjunction, and p is being denied, q is being denied. Here's an example from page 98 of the textbook. It is not both hot and snowing. That's logically equivalent to either it is not hot or it is not snowing. Let's think about it. Hot and snowing. So if we symbolize that, we would have H and S. If that statement is true, what does that mean? Well, clearly it means H is true, hot, and S is true, snowing. So this is true insofar as H is true and S is true. But if we deny that, we say it's not the case, or in other words, what makes it false to say it's both hot and snowing? Well, then either it is not hot or it is not snowing, or both. So that's logically equivalent to not H or not S. So once again, think of it this way. If this statement is true, H and S, but then we say it's false, the only way it's false is if either H is false or S is false, or both are false. So hence, from this statement, it is not both hot and snowing, we can immediately infer that either it is not hot or it is not snowing. And that makes sense. Here's another example. It is not either raining or sunny. That's logically equivalent to it is not raining and is not sunny. So from here, raining or sunny. So that's R or S. If that's true, that means either R is true or S is true or both are true. But if we deny that and say it's not the case, what does that mean? What makes it not the case that it's either raining or sunny? Well, it couldn't be raining and it couldn't be sunny, so not R and not S. If it's not raining or sunny, then it must not be raining, it must not be sunny. So from this or to this and. Let's step back again. So let's think about moving from the so-called left-hand side to the right-hand side. So from this side here to this side. So first we negate the entire conjunction or disjunction as a whole. So here we have a conjunction, P and Q, and we're negating it. And also notice the change from a conjunction to a disjunction or vice versa. So here you have a conjunction, here you have a disjunction. And also notice that we negate each member of the initial conjunction or disjunction. So here, not P, not Q. And also, we may have to do some double negation in practice. When it comes to De Morgan's law, understand why this statement is identical with this statement. Don't just memorize those symbols blindly, but really understand them. Turning to page 101, what can you conclude from the following premises using De Morgan's laws? For example, number 2, it is not the case that Either air is a good conductor of heat or water is a good conductor of heat. Apply De Morgan, what do you get? Well, you would get air is not a good conductor of heat and water is not a good conductor of heat. Think about this verbally. Think about this symbolically, and then you will absorb De Morgan's law in a crystal clear way. Essentially, we went from not parentheses x or y, close parentheses, to not x and not y. Number 4, the Mississippi River does not flow northward and the Nile River does not flow southward. Apply De Morgan, what do you get? Well, we would get it is not the case that the Mississippi River flows northward or the Nile River flows southward. In other words, we've essentially went from not x and not y to it is not the case that parentheses x or y, close parentheses. Now, the danger with these problems is applying a law blindly or algorithmically without thinking about what is really going on. Indeed, for a dummy like me, I like to stop and evaluate what I'm doing to make sure it makes sense. And that's how you learn this material in a deep sense, in a deep conceptual sense. You then don't forget this stuff 2 weeks after an exam. So this is just part C of exercise 16. We'll do some of the problems. We just want to apply De Morgan. So number 1 is straightforward because we just did this very recently. So we have a conjunction that's being denied. So we know that's just logically equivalent to the disjunction, not P or not Q. Number 2 is a little bit more interesting. We have the disjunction, the or sentential connective. We have not R or not T. What would that be logically equivalent to? It would have to be not parentheses R and T. So we moved from a disjunction to a conjunction. But let's think about this left-hand side, not R or not T. It's telling us that R is not the case or T is not the case. Or in other words, R and T cannot both be the case. So we can think about moving from the left-hand side to the right-hand side in that way. For number 3, we have our conjunction not R and S, and that's being denied. We're going to move to a disjunction then. We'll say this is logically equivalent to not R or not S. So this not R is being denied. We have this double negation, and so this is logically equivalent to R or not S. Hence, if it is not the case that not R and S is the case, that just means R or not S is the case. Notice the double negation there. Number 4 has the same formal structure, so to speak, as number 2. We just have this not G or not H. Hence, this is logically equivalent to, it is not the case that G and H is the case. That is to say, if G is not the case or if H is not the case, then G and H cannot both be the case. For number 7, we have a conjunction not P and not Q. So this would be logically equivalent to, we're moving to a disjunction. So not parentheses, not P or Q. By the way, this could also, the textbook was kind of nice because we have this not P. So we know that we're going to end up here with a not P, but the textbook could have said P and not Q, and this is also the same thing as this, and the same thing as this here. Number 8 is straightforward. We have this disjunction, and it's, so to speak, being collectively denied, so this is equivalent to not C and not D. For number 9, we have this conjunction here, and it's being denied, so we're going to be moving to a disjunction, and we'll deny each individual term. So we have this is logically equivalent to not P or not Q, but by double negation, that's logically equivalent to P or Q. For number 10, we have this disjunction, not S or not T. So we're going to be moving to a conjunction, and that conjunction is going to be collectively denied. So this is logically equivalent to, it is not the case that S and not T. So note, of course, that this not S here became S. This not T, well, what we're doing is we're considering this not T here. Well, that was probably awkwardly put, but in other words, let's say we had not S or T. That's logically equivalent to not S or not T because of by double negation, but that would just be equivalent to not parentheses S and not T close parentheses. Okay. And now let's turn to part D of exercise 16, pages 101 to 102. We will do all the problems here. These are formal proofs. For number 1, we want to prove that S is not the case, not S. Given 4 premises, the first thing I'd like to do is to look for something that is, so to speak, categorically stated. Now, premise 1, we're told that it is not the case that P and Q are the case. So we can use that, and I think we should apply De Morgan's rule, or De Morgan's law. So for line 5, we can get not P or not Q. So De Morgan, line 1. Now notice we have not P or not Q. Not P appears in the antecedent to a conditional, and not Q appears in the antecedent to a conditional. And so we'll get T, or we'll get T. So for line 6, we can say T or T by our constructive dilemma, lines 2, 3, and 5. But if we have T or T, that means T must in fact be the case. Hence for line 7, we'll say T by our tautology, line 6. Not T appears in the consequent of a conditional. So for line 8, let's double negate T. So double negation, line 7. We have not T, that denies this consequent, so we can thereby deny the antecedent. Hence for 9, therefore it does follow not S by Modus Tollens, lines 4 and 8. Number 2, we want to prove it is not the case that A or B is the case. So not parentheses A or B, close parentheses. Line 1, which is a premise, we have a conjunction C and not D. We can get C by simplification. So for line 4, C simplification, line 1. And then C appears in the antecedent. We can affirm that to affirm the consequent. C is sufficient for not A being the case. Line 5, not A, Modus Ponens, 2, and 4. Line 1, we have this not D. For line 6, we could say not D and C by the commutative rule. Line 1, for 7, we can get not D by the simplification of 6. Because notice we have this disjunction here, D or not B, but D is not the case, so therefore not B must be the case. Hence for 8, we'll say not B, Disjunctive Syllogism, 3 and 7. We want to prove this statement here. We have not A on line 5, we have not B on line 8, so let's just combine them. So for 9, we can say not A and not B, conjunction, lines 5 and 8. But notice this statement here and this statement here are equivalent. We just have to use De Morgan. So for 10, therefore, it's not the case that parentheses A or B, close parentheses, De Morgan, line 9, and that proves that. Now we want to prove the conjunction R and Q. Let's look at what we have. Well, line 3, we have this not S, so we can affirm the antecedent to get that consequent through Modus Ponens. Hence, for line 4, we have not parentheses P or not T, close parentheses, Modus Ponens, lines 1 and 3. I think the wise course is to use De Morgan. Then we can just state it in an equivalent fashion, get rid of the parentheses there and so forth. So then we have terms we can analyze, or we can use. Okay, right now we can't use this for anything, so if we have a conjunction, then that's going to help a lot. So for line 5, we can say not P and not T, De Morgan 4. Then for 6, we can say not P and T by the simplification, the double negation of 5. So we went from not T to T. Okay, so now what can we do? We have T appearing on line 2 in the antecedent, so let's eventually simplify. So for line 7, we can say T and not P, commutative rule, line 6, and then for 8 we can get T by the simplification. Sorry, the stylus pen is kind of going out, by line 7. And then for 9 we can get Q and R modus ponens, lines 2 and 8. For the Suppes and Hill textbook, by default the if-then sentential connective is strongest, so implicitly there's really parentheses there, so we could get that Q and R. We want to prove R and Q, so for 10 we just resort to the commutative rule. So now we have R and Q, commutative rule or commutative law, line 9, and that concludes that proof. Number 4, we want to prove not R. Our premises, we have a conditional, a conditional, a conditional, a conditional. The question to ask, is there any overlap? Do we have a hypothetical syllogism? And we do, with lines 1 and 2. If P, then not Q, but if not Q, then not S. So for line 5, let's say if P, then not S, by our hypothetical syllogism with lines 1 and 2. And notice we have this if P, then not S as an antecedent to a big conditional, and we know that in fact is the case, so we could affirm that. Hence for line 6, we can say not T by modus ponens with lines 3 and 5. But because we know T is not the case, we can deny the consequent there to thereby deny the antecedent, because the consequent is necessary for that antecedent. So for line 7, it does follow that therefore not R by modus tollens with lines 4 and 6. For number 5, we want to prove D. Let's see what we have. We have 4 premises. Nothing, so to speak, categorically declared to be the case in an absolute sense. However, we do know that at least C or not A is the case. And likewise, we know at least not B or D is the case. However, note that if C is the case, then B will be the case. If not A is the case, then B will be the case. We have a constructive dilemma. And so for line 5, we'll say B or B, constructive dilemma, lines 1, 2, and 3. For 6, we can then get B, because we have a tautology, line 5. B contradicts not B, so for 7, let's double negate, so not B, double negation 6, so that's not the case, and so 8, therefore it follows D is the case, because we have a disjunctive syllogism, lines 4 and 7. For number 6, we want to prove not T. We have 4 premises once again. Let's see. Well, we do have a constructive dilemma, it looks like, because we have this disjunction, R or Q, but if R, then not S, if Q, then not P. And so for line 5, we can get not P or not S, constructive dilemma, lines 2, 3, 4. It looks like we're going to have to do some kind of Modus Tollens inference eventually, because look at here, premise 1, and this looks very close to this, doesn't it? let's do De Morgan. So for 6, we can say it's not the case that, parentheses, P and S, close parentheses, so De Morgan, line 5, and then this statement is denying this statement, so we can deny that antecedent. And so for 7, therefore, not T, Modus Tollens, lines 1 and 6. For number 7, we want to prove not P. We're given 4 premises to work with. We have a conditional, a disjunction, a conditional, and a conjunction. Let's see if we can work with that conjunction. We have this not Q and not U. Well, that looks very similar to this statement here, Q or U. For line 5, then, we should try De Morgan. So this is equivalent to, it's not the case that, parentheses, Q or U. So that's just De Morgan, line 4. And this statement denies this consequent, so we can deny the antecedent. So for 6, T is not the case. We know that by Modus Tollens, lines 3 and 5. Line 2, we have a disjunction. We have the or sentential connective. T appears here. We can deny that. So depending on the textbook right now, we might be able to say R and S is the case, but some textbooks would require us to do the commutative rule first, so I'm just going to do that for the heck of it. Line 7, we can say T or parentheses R and S, so the commutative rule, line 2, and then we can deny that T. So for 8, we can get R and S because we have a disjunctive syllogism, lines 6 and 7. And now what? Well, we do have, oops, sorry. Oh, I see. Okay, we have this R here. Then we can get that not P. So let's simplify. So for 9, we can get R by the simplification of line 8. And then for 10, we could affirm that therefore not P by Modus Ponens, lines 1 and 9. For 8, we want to prove the conjunction R and Q. And let's see, we have this disjunction here, P or Q. Well, P appears here in the antecedent, Q appears here in another antecedent, so we could get S or S because we have a constructive dilemma. Line 5, S or S, constructive dilemma, lines 1, 3, and 4. So S must be the case because we have a tautology, line 5. And S appears in the antecedent to a conditional, so we could affirm that consequent. So for line 7, we have Q and R by Modus Ponens, lines 2 and 6. We want to prove R and Q. Well, we can do that, and we can justify that by the commutative rule. So therefore, R and Q, commutative rule, line 7. For 9, we want to prove the disjunction G or not H. And let's see. Well, we do have J or K. Looks like we have another constructive dilemma because if J is a case, then E is a case. If K is a case, then F is a case. We'll say E or F because we have a constructive dilemma 2, 3, and 4. And that appears as the antecedent. And remember, with the Suppes and Hill textbook, the default is the conditional has the strongest sentential, well, it's the strongest sentential connective by default. So implicitly, at least for the Suppes and Hill textbook, there are parentheses there. So we could affirm the antecedent to get that consequent, not H, Modus Ponens, lines 1 and 5. We're almost there. We want to have a G, so or G. Not or G, but or the letter G, the symbol G. So for 7, we can say not H or the atomic sentence G, because this is the addition law, line 6. Because not H is true, you can put it in a disjunctive relationship with anything. And then for line 8, we'll just resort to the commutative rule to get G or not H. So commutative rule, line 7, and that concludes that proof. The last formal proof, we want to prove the conjunction S and T, We're given 4 premises to work with. It looks like premise 2, 3, and 4 we can't do anything yet, but premise 1 we could apply De Morgan's rule. And hence for line 5 we'll say not P and not R. De Morgan, line 1. And then we could double negate to clean this up, so to speak. So for 6, not P and R, double negation 5. We know R is the case. That appears as the antecedent to a conditional. So let's get R and not P by the commutative rule, line 6. And then for 8 we can get R by the simplification of 7. We could affirm this antecedent to affirm that consequent. So for 9, S, Modus Ponens, lines 3 and 8. We want to prove that S and T is the case. We have this T and S here, so that means we're going to eventually want to affirm this antecedent. And that means we better get Q somehow. Now Q appears here, line 2. Moreover, we know that P is not the case. So for line 10, we could do this. We could say P or Q, commutative rule, line 2. And then from line 6, we can get not P by simplification. So for 11, we'll get not P, simplification, 6. And then we could deny this to affirm that Q. So for 12, we get Q, disjunctive syllogism, 10, 11. So now we have our Q, we have our S, so let's combine them together. 13, we can get Q and S by the conjunction rule, lines 9, 12. And then we could affirm that antecedent to get the consequent, so 14, T and S, Modus Ponens, 4, 13. We want to prove S and T. We don't have that yet, but we can justify the statement S and T by the commutative rule using line 14, and that concludes the proof. Thank you for watching, and up next we're going to review section 2.5, but in particular we're going to cover more rules of inference. Well, strictly speaking, most of it will be additional equivalencies that are not covered by the Suppes and Hill textbook. It's bonus material, but a lot of other textbooks do cover it, so I think we should too. That'll be up next, and I'll see you then. Bye for now.